Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon to all viewers. Welcome to the 8th series of Research and Innovation webinar, School of Electrical Engineering. I'm Sherry, your moderator for today's session. This program are brought to you live from School of Electrical Engineering, Faculty of Engineering, University Technology Malaysia, Johor Bahru's Facebook. Without further ado, I would like to invite Professor Dr. Muhammad Kamal Ibrahim, the Associate Chair of Research and Academic Staff, to give a short opening, as well as introduce our guest speaker, Associate Professor Dr. Nik Rumzi Nik Idris, the Head of Power, Electronics and Drives Research Group. Over to you, Prof.
Okay, thank you very much, Puan Syari Huzaima, for introducing this event. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and salam sejahtera to all viewers. Thank you once again to all viewers that follow this webinar through our FB Live School of Electrical Engineering. My name is Professor Muhammad Kamal Ibrahim. I'm the Associate Chair of Research and Academic Staff, School of Electrical Engineering, University of Malaysia. Our topic is today entitled Power Electronics and Applications, that will be given by Head of Power Electronics and Drive Groups, Associate Professor Dr. Nik Rumzi Nik Idris. Before he gave his presentation, I would like to introduce our speaker today. For your information, please share, like, and comment on our FB Live School of Electrical Engineering. Dr. Nik Rumzi Nik Idris received a Bachelor in Engineering Electric Honours from University of Wollongong, New South Wales, Australia in 1989, and a Master degree in Power Electronics from Bradford University, United Kingdom in 1993, and a PhD degree from UTM in 2001. Before joining UTM, he was with Proton as a research engineer and later with IBM Malaysia as a services engineer. He joined University of Malaysia in 1992 and is currently an associate professor and the head of Power Electronics and Drive Research Groups at the School of Electrical Engineering, University of Technology Malaysia. He is also the head of UTM Proton Future Drive Laboratory in University of Technology Malaysia, Skudai. He has published more than 160 papers in journals and conference proceedings in the area of power electronics and motor drive. He was a visiting researcher at the University of Akron, Ohio in 2002 and was the chair of IEEE Power Electronics Society Malaysia chapter from 2014 to 2016. He is a senior member of the IEEE, and his current research interests include control of AC motor drive and electrical vehicle system. About our webinar today, this webinar is divided into two parts. The first part gives the introductions to power electronics and its application is renewable energy system and electric vehicles. And the second part is more on the webinar, introduce the power electronic and drive research group and the research activities of the group. Now, I would like to invite Dr. Nik Rumzi Nik Idris to give his webinar on power electronics and applications. Over to you, Associate Professor Dr. Nik Rumzi Nik Idris.
Thank you, Prof. Kamal, for the nice introduction. My presentation for today is going to be divided into two parts. The first part, I will talk about the power electronics and what is powertronics, and I'm going to share with you why we need the power electronics in our daily lives. And then I'm going to talk about some of the applications of the power electronics in the area of renewable energy and electric vehicles. And then the second part of the presentation, I'm going to talk about the groups of power electronics and drives research group and their activities, related activities. So what is power electronics? Powertronics is one of the field of electrical engineering that deals with applications of power semiconductor devices and for the control and conversions of electric power. If you look at the definitions of power electronics in most of the textbook, you will see that there are three main keywords that include in the definitions of these power electronic systems, which are the power semiconductor devices, the control, and the conversions of electric power. And the Powertronic system is best described using the plot diagram, which is what I'm going to do now. At the heart of the Powertronic system is what we call the power electronic converters. And we have the input to these power electronic converters, which can be of in the form of AC or DC, which is typically unregulated. The output is then will be connected to the load. And typically we want to control the output of the load. We want to control the magnitude of the voltage or the frequency of the voltage, which means that we do that by using the controller, which is connected to these power electronic converters. And we're going to have some reference. Normally, we want to fix the output voltage to a fixed value, regardless of the variations in the input voltage or the variations in the load, which means that we need to have some sort of feedback to the system that fix the output voltage output variables and then processed by the controller, which will then generate the switching signals, which is then fed to the power electronic system, power electronic converters. Share. Hold on. Share.
Betul ni di sini?
Hah?
Di sini? Di sini.
Tak, saya pakai set itu.
Ini.
Ya.
Sebab itu betul ni share.
Ada.
Kau senjak dari mana? Senjak nyari.
To all our viewers, we are very sorry we have some technical hiccups, and we will be back in a short moment. Thank you for your patience.
Ya. Mana pergi tadi? On kan? Alright. Sorry for the technical problems. My presentation. The first part is going to be on the explanations of the power electronic systems and the applications of the power system in the area of renewable energies and electric vehicles. And the second part of the presentation is going to be on the power electronics and drive research group itself. And I'm going to talk about the research and activities of the group. Okay, the field of what is power electronics? Power electronics is the field of electrical engineering that deals with the applications of power semiconductor devices and the control of and conversions of electric power. There are three keywords in this definition, which is the power semiconductor devices, the control, and the conversions of electric power, which is best described using the block diagrams. The heart of the power electronic system is the power electronic converters, and you have the input source, which can be an AC or DC voltage, which is typically unregulated. The output is then connected to the load, which can be DC or AC, and normally we want to control the output to certain values of frequencies or magnitude, and we do that by using the controller, which has a reference value. And most of the time, we want to fix the output voltage to a certain frequency or magnitude voltage, regardless of the variations in the input or the variations in the load, which means that we have to have some sort of feedback system that will process the signals and generate the suitable control signals. The heart of the power electronic system is the power converters, which mainly consists of the several elements. This is hold on. Seems not working here. Excuse me. The system is not working. Hold on. It's supposed to display the passive devices here. You know, the left-hand side arrow is supposed to display the passive devices, and the middle arrow is supposed to display the high-frequency transformer, and the right-hand side arrow is displaying the semiconductor devices, which is operated as a switch. So these are the three elements of the power electronics converters. The main difference between the power electronic systems and the other linear system is that in power electronic system, the power semiconductor devices is operated as a switch, which is either on or off. And we know that if it is in the on state, and then the voltage across the switch is going to be equals to 0. And if it is in the off state, then the current through it is going to be equals to 0. So in either case, the power losses associated with the switch is going to be equals to 0. So what we have here is a very high efficiency system. Okay, we have a passive devices, which are the inductor and the capacitor, which typically has a very low losses just because of the parasitic resistance, for example. Then we have a very high switching frequency transformer, again with a very low switching power losses. And then we have the semiconductor devices, which is also have a very low switching losses, which is mainly due to the leakage current and the forward voltage drop, as well as the switching frequency losses. Okay, so the ratings of the power electronics can be from a fraction of watts up to gigawatts, which is normally applied for the DC transmission systems. So why do we need power electronic systems? Excuse me. I think we need to stop because it's supposed to be displaying the graph here, but it's not displaying the graph. There's something wrong with the. Can we just? I will try to load a new PowerPoint presentation in that case. Sorry about this problem here. Just bear with me. Just 1 second. All right. 1 second. Okay. Right. Okay, I think we can continue now. Sorry about the interruptions and technical problems we have here. Let's look at on the energy scenario of the world. Currently, not currently, but in 2017, which is extracted from IEA website here, the electricity generation is mainly obtained from the fossil fuel, which are the coal, gas, and oil. 10% is coming from the nuclear power, which we know have some issues related to the safety, and then another 25% is coming from the renewable energy. If you look at the depletion curve of the fossil fuel, you can see that sooner or later, these fossil fuel sources will be depleted, as can be seen from the depletion curve that roughly about 200 years from now, coal will be depleted, and then we have oil, which is going to be depleted in about 100 years from now, and the gas is going to be depleted around 150 years from now. We probably will not be experiencing these depletions of the fossil fuel, but probably our next generations, which is our children or grandchildren, will probably experience these depletions of the fossil fuel. So what can we do about that? Well, we can actually flatten the curve, which means that we can extend the range of this availability of this fossil fuel over a longer period, which is not really a good choice, because fossil fuel actually is the main problems is actually producing the greenhouse gas. But anyway, if we decide to do that, then what we can do is we can conserve the energy, savings the energy. And how do we do that? Well, we can use the power electronic equipment or devices which known to have a very high efficiency. An alternative way is to increase the use of the renewable energy resources. And in case of the renewable energy, it will be never depleted, because as long as there is sun, then the energy will always be there. However, in order to utilize this energy, we still need the power electronic technology in order to convert the energy into a useful form which is suitable for our loads. So the problem is that when we burn this fossil fuel to produce the electricity, then we are actually emitting the various types of gas, poisonous gas, such as the sulfur dioxide, the carbon monoxide, and a huge amount of carbon dioxide, CO2. And this CO2 is known to be the greenhouse gas, which is capable of trapping heat from leaving the atmosphere of the Earth, which is causing the global warming. The greenhouse gas naturally is good because it actually keeps our Earth to the right temperature with an average value of 15 degrees Celsius. Because according to the scientists, without this greenhouse gas, our Earth will be very much cold at about minus 18 degrees Celsius. However, the problem is that there is too much greenhouse gas or CO2 nowadays, which is produced by men, okay, which causes more heat to be trapped in the atmosphere, and which causes the temperature of the Earth to increase. This is the graph of showing the global surface temperature of the Earth as from 1880 to 2020. As you can see, that the gradual increase of the temperature from the pre-industrial era, which is in the I think it's 18th century, mid 18th century, until now 2020, we have a gradual increase in the temperature, which is caused by the human drivers. And it is confirmed by the IPCC, which is the Intergovernmental Party panel of the climate change, that this increase in the temperature is basically caused by the man-made greenhouse gas, which is CO2. And who is actually the culprit to this increment of the CO2? Well, if you look at the graph here, the main culprit is actually the developed nations, United States, which is producing the highest per capita CO2 from 2000 to 2018, and followed by the rest of the country. China also is contributing to this CO2, and in fact, if you look at the total fossil fuel contributions of the world, according to the country here, China is the highest of all because of its large population, which is around 1.39 billion. Okay, so overall, the total CO2 emitted by China is the highest, as you can see there, which is followed by the United States, European countries, India, and the rest of the world. So what happens when the Earth gets hotter? There are a lot of things can happen, but what we can think of right away is that the ice at the North and South Pole is going to melt. And this will cause an increase in the sea level. And it is predicted by IPCC that, which is based on the data obtained in 2014, that by 2100, the sea level will increase by 0.6 meter, which is also the reason why Indonesia is moving its capital from Java Island to Kalimantan. And it will cause a warmer oceans, which will expand, which means that the ocean will expand, and that would also contribute to the rise of the sea level. And it will cause more evaporations. There will be some parts of the world, there will be extreme droughts, and some part of the world will be flooded, with extreme weather, stronger storms, which normally portrayed in the Hollywood movie. And this phenomenon is what we call the climate change, okay, which is caused by the global warming, which is something that Donald Trump does not believe in, because during his presidential campaign, he used to say that global warming and climate change is just a hoax, is a political agenda, which is the reason why United States is pulling out from the Paris Agreement in 2017. So the system which defines the climate of the world is very complex, and it is interconnected to one another, as shown by these diagrams here. It starts with the increase of the temperature of the Earth, which is caused by the greenhouse gas, causes the more evaporations, warmer oceans, melting snows, which cause the Earth to absorb more energy, and which is causing the more increase of the Earth temperature. If you look here, this is a positive feedback loop here, which is very dangerous and scary actually. Okay, and it can also cause the other changes in the plants and the animals habitats and so on. So what can we do about that? How can we mitigate this global warming and climate change? There are many ways that we can do. In the context of using the power electronics, then what we can do is that we can reduce the generations of the greenhouse gas, GHG, and we do that by reducing the utilizations of the fossil fuel-based energy, and we can do that by using power electronic systems. Okay, because we know that power electronic systems is a very high efficient, which means that for a given output, a system without power electronics will consume more energy compared to the system which uses power electronic systems. Some quick examples on what we can do to readily apply to our house. Sorry? Full screen. It's already full screen. Saya tak tahu how. It's already. There are too many glitches today. I'm not sure why. But let me just continue with what I just said just now. Some quick example that we can readily apply to our house is that we can change our lighting system in our house. You know, we used to use the incandescent light in our house, which are practically banned in some other countries, including Malaysia. I think in Malaysia has stopped the productions, the import, and the sales of incandescent light since 2014, which is known to have a very poor efficiency in converting electricity to the light energy, because most of the energy is converted to heat. Then we move to the fluorescent light or fluorescent lamp, and then there is a compact fluorescent lamp or CFL, which is more compact which does not use the low frequency bulky ballast, but rather use the high frequency and power electronic circuits in order to operate, which is 5 more efficient than the incandescent light. And then more recently, there is a LED lamp, which is 50% more efficient than CFL. Okay, we have the incandescent light, fluorescent light or lamp. Then we have the CFL and the LED lights or lamp. These two lights, CFL and the LED, basically uses power electronic circuits in order to operate. An example of this is that we have the input AC here, which is first converted to DC, and then is fed to the power factor correction circuit in order to improve the power factor caused by the AC to DC converter, which is then fed to the DC-DC converter to reduce the voltage to a level which is suitable for the LED lamps. The isolations can be implemented inside using this isolated DC-DC converter, for example, using the forward converter, using the high frequency transformer. And then each of the parallel connected, series connected LED here, we have a PWM current control circuit here in order to control the current to a fixed value, because LED is known to be very sensitive to the current flow through it. With a very slight change in the current, the brightness and the color of the LED can change. So therefore, again, we need a power electronic circuits here in order to maintain a constant current. Another example is to apply this to our air conditioning system or refrigerator. Okay, we used to use the air conditioning system with the conventional method of controlling the temperature by on and turning off the compressor, which is not really efficient, because every time we turn on the compressor, what happens is that we have a very large current surge, which causes high losses. And in order to avoid these losses due to the turn on and turn off of the compressor, what we can do is that we can control the speed of the compressor to match our temperature requirements, which means that instead of controlling the on-off of the compressor, we do it by controlling the speed of the compressor. And we can do this by using the power electronics converters. An example of this is shown here, where you have the AC source, AC main here, and then you have the AC to DC power electronic converters, which is then fed to the inverter, which is fed to the motor compressor, which can be a BLDC or induction motor, in which the voltage and the current here is varied. And of course, we have the controller, which will controlling the switching functions of this inverter, where we have the reference and the feedback temperature, and as well as the voltage, the current feedback. Now let's go into example of using the power electronic converters for the renewable energy system, and I'm just going to concentrate on the wind energy and the PV, solar PV, because these two sources of renewable energy has the highest growth compared to the other renewable energy sources. Let's look at on the wind energy first. This graph shows the cumulative capacity of the wind power in the world currently up to 2018. We can see that the growth of the power, which is generated by the wind turbine, can be seen to be almost exponentially growth. Okay, which is very, very encouraging here. And this is also the same different graph which shows the capacity of the wind power for a different country, for selected countries. We have a China here, we have the United States, and we have the rest of the world here. China is currently producing about 240 gigawatts of wind power from out of nearly 600 gigawatts compared to the rest of the world, which is very huge. And then we have the United States, which is following next, is around 100 gigawatts of wind power, and then followed by the rest of the world. This is the renewable, the wind turbine energy systems, which is used to generate the electricity and connect it and feed it to the grid system. We have the wind turbine here, which is used to convert the wind energy to the mechanical energy. Then we have a gear system, which is used to increase the speed of rotations to a speed which is suitable for the generator system, which can be a double effect induction generator, a squirrel cage induction generator, or the permanent magnet synchronous generator. And then we have the power electronic converters here, which is used to convert the voltage generated by the generator, which is unpredictable depending on the wind available, depending on the speed of the wind, into a more stable voltage and current and frequency, which can be fed to the grid system using the low frequency transformer here. This is one of the example of the wind energy systems where where it uses the double effect induction generator here. The stator of the generator is connected to the grid via the transformer, and the rotor of the generator is connected to the power electronic converters via the slip rings. For a given speed wind, there is a critical or a specific or a unique value of speed of the generator or the turbine that can extract the maximum power from the wind, which means that in order to extract the maximum power from the wind, we have to control the speed of the generator, which is what is performed by these converters here. The generator side of the converter which is the AC to DC, is normally controlled using the field-oriented control techniques, which is oriented to the stator flux, in which the rotor, the D and the Q axis of the rotor current will control the reactive and the active power of the generator, which is the torque, in order to control the speed to extract the maximum power from the wind turbine. And we have the grid side of the converter, which is the inverter, which will maintain the constant voltage, DC constant voltage, and at the same time will inject the reactive and the active power to the grid, which is determined by the grid requirement. This type of configurations of wind turbine is known as the type 3 configurations. And then we have a type 4 here, which uses the permanent magnet synchronous generator, again connected to the power converters here, or it can also be a squirrel cage induction generator. And we have the options of eliminating the gearbox here, because if we use a multiple machines or generator here, then the speed can be operated very low. We don't need the gearbox in order to increase the speed of the generator. Again, this generator side inverter is used to control the speed of the generator to extract the maximum power, and the grid side of the converter is used to inject the active and reactive power to the grid, and at the same time maintaining the constant DC link voltage. Okay, if we interconnect the wind turbine, then we form what we call the wind farm. This is one example of the wind farm located in the China, which is one of the largest in the world. Gansu, China, which has a capacity of 20 gigawatt, okay, which is fully operated in 2020. If we have a generator connected in series or parallel, then we have several options to do that. You know, you have the options of parallel AC connections with high AC voltage transmission, which is typically used for the onshore farm, where the farm is close to the grid system. We have the options of connecting the wind farm using the high voltage DC transmissions, in which which is normally used for the farm which is located far from the land. And then we have the onshore farm substation here, which is then convert the DC voltage to the AC, which is then connected to the AC grid. And we also have the options of using this also typically used for the offshore farm, but instead of using the low frequency transformer for the medium voltage AC collection voltage here, we use the DC voltage here, okay, which means that we avoid low frequency transformer, and the Powertronics the Powertronics system is going to be more compact. And again, we use the high voltage DC transmission to transmit the power from the offshore to the onshore. If we connect the wind farm or wind turbine in series, then we can form a voltage which is high enough to be transmitted to the DC using the DC voltage transmission system, which means that we don't need the DC to DC to boost the voltage. Okay, this is one example of the huge wind turbine, which is I think the largest in the world currently, which produce 12 megawatt of wind of electricity. You can see the size there, the small size of the people. This is the blade of the rotor, which expands to the length of 110 meters, which means that the radius of the rotor of the blade is going to be 220 meters, which is very, very huge. Let's move to the next applications of Powertronics. Again, also in the area of the renewable energy, and we look at the solar PV now. Again, I'm showing here the graph of the amounts of gigawatts power produced by the solar PV in the world, which is also contained the information of the various countries here. As you can see here, the China, which is in the green there, again produces the largest compared to the rest of the world. Okay, which is, and then we have followed by the United States, the Japan, Germany, and India. Currently, the PV solar in the world producing about 505 gigawatts of electricity around the world. This is according to the data obtained in 2018. This is a different graph showing the countries, the power which is generated by the countries. Again, we can see that China is now currently in 2019, last year, according to the data here, produced 204 gigawatts of capacity, has a 204 gigawatt capacity for the solar PV, which is left far behind the United States, which only produce about 76 gigawatts, have a capacity of around 76 gigawatts, and followed by the rest of the country here. For the record, Malaysia only have 0.882 gigawatts, which is less than 1 gigawatt, which is very difficult to fit into this graph here because it is less than 1 gigawatt there. These are the the increased interest in the use of this PV solar is basically because of the falling price of the PV itself. You can see that here from 1977, the price of the PV used to cost $76 per watt, and nowadays it is less than $1 per watt. Okay, this is a typical characteristics of the PV panel, PV module, which shows the voltage and the current characteristics in the blue curve here. which depends on the solar irradiance. If you multiply the voltage and the current of the characteristics of this PV, then you will get the power, okay, the power which is produced by the PV. And as you can see that the power is shifted as the irradiance changes, okay, which means that in order to track this maximum power that that can be extracted from the PV, we need to keep track of this maximum power, and we typically do this using the maximum power point tracking algorithm, which is normally implemented in the power electronic converters. Okay, this is a typical grid-connected system, a solar PV system. We have a solar power, a solar PV panel here, which is connected to the DC-DC converter, which will boost the voltage before it is connected to the DC to AC converter, which is the inverter, and then connected to the grid via the transformer. We have the optional of removing that low-frequency transformer and implemented the galvanic isolation inside that DC-DC converter, which can be, for example, using the flyback converter. The MPPT algorithm is typically implemented using this DC-DC converter. This two-stage PV conversion stage PV system is normally applicable to the industrial and domestic applications. Next here is shown the single-stage PV, which is typically used for a large PV farm, where you have more PV connected in series, which means that you can generate the enough voltage to be converted to the AC, which is then can be connected to the grid system. You don't need to boost the voltage here, and the MPPT, the maximum power point tracking, is performed using this DC to AC converter. There. For standalone application, we normally have to have the energy storage devices, which can be of several configurations. What is shown here, the energy storage, which is the battery, is just simply connected to the DC link between the DC-DC to the DC-AC converter, which is then converted to the AC using the inverter here, which can be either a single phase or the three-phase transformer. So the DC-DC converter here is used to protect the battery from overcharging during the daylight, and also to keep track of the maximum power which can be extracted from the panel. And the inverter here is normally used to provide the regulated AC voltage, as well as to protect the battery from over discharging when we use the power from the battery. Okay, let's look at the final applications here, which is the electric vehicles applications. What is shown here is the timeline of the electric vehicles starting from 1890 to 2020. You can see here that the electric vehicles is basically invented a long time ago in the 19th century. And we have two surges here during the early 20th century, late 19th century, and we have another surge here, which is in the late 20th century. Okay, this interest, the surge of interest in the electric vehicles during these two periods is for the different reasons. Okay, during the first surge, which is which is peaking at 1920, the electric vehicles is typically used because of the problems with the internal combustion engine, or ICE, which is at that time is noisy, which is dirty, oily, and you have to use a manual crank in order to start the vehicles. And people prefer electric vehicles at that time, which uses a rheostat rather than Powertronics, and DC motor and DC and a lead acid battery. And then the ICE get improved, and which means that you no longer require manual cranking to start the ICE. And as you can see that from 1924 up to the early 1960s, you have a complete blackout of the electric vehicles there. Okay, but then again, the interest surged again in the late 20th century for a different reason. Now the interest is because of the environmental concerns, which is what we have discussed before, mainly the global warming and the climate change. This is the graph pie chart of showing the productions of the greenhouse gas, which is mainly CO2, produced by the different sector. What I want to highlight is the transport sector here, which contribute almost 15%, and the road transport alone contribute about 12.1% to the emissions of the greenhouse gas. And in Malaysia, according to a study conducted by a local researcher in 2015, the road transport alone contribute to 21% of the overall CO2 emitted in Malaysia, which is higher than the average values of the world, which means that it is very important for us to consider using the alternative transport systems rather than using the fossil fuel-based vehicles. Okay, before we go into the details of the Powertronics we use in the electric vehicles, let's just go very quickly on the architecture of the electric vehicles. Shown here, which is a separate motor, gearbox, and the differential. We have a electric motor here, and which is connected to the gearbox, which normally used to reduce the speed of the electric motor, which is then connected to the differential, which will provide the different speed between the left and right speed. This is a separate motor, gearbox, and differential configurations. Alternatively, we can have everything mounted on the same shaft, which is a drive shaft here, which is shown here. We have everything mounted on the same shaft, the gearbox, the motor, and the differential. A better way or smarter way is to use a separate motor for the wheel, which means that we don't need the differential in order to provide the different speed of the wheels. Okay, because we can control the speed of the wheel independently, during the turning and so on. In this case, the gearbox and the motor is placed close to the wheel. A better way is to include the gearbox inside the wheels, and the motor is mounted outside the wheel. Okay, and the ultimate way is, of course, to mount everything inside the wheel, which means that we have the motor, and we don't need the gearbox here, we don't need the differential here, because we can control the speed, the motor, which is the wheel, independently. Okay, and if we do that, then we have a four-wheel drive. We can configure it as a four-wheel drive. One example of such wheel, which is a very expensive wheel, is shown here. You have a rotor, you have a stator, and you have a power electronics here, which is mounted, package everything inside the wheel, which is obtained here from the Protein Electric, one of the leading manufacturer of in-wheel motor. Regardless of the architecture of the EV, you still need the basic components to form an electric vehicle, which is the energy sources, the power electronics, and the motor. Okay, what is shown here is the architecture for the battery electric vehicle systems, which consists of the battery pack here, which is supplying the power to the inverter, which is then converting the variable voltage and variable frequency, which is used to control the AC motor. If we use this configuration or architecture, which uses a single energy storage, then we are stressing the battery, because every time we do the accelerations, then we need to extract huge amount of current from the battery, and every time we do the braking, in which the kinetic energy is converted back to the electric, then the battery is will be charged. And not all kinetic energy can be captured by the battery, because the battery has its limited current in order to be charged. In order to improve this, what we can do is that we can incorporate the hybrid energy storage, which means that we include another different type of energy storage devices. And there are several choices that we can have. We can have the supercapacitors, can have fuel cells, or can have the batteries. Okay, this is the specific energy and the specific power for these different devices here. What I want to highlight is the supercapacitor here, which has a much higher specific power compared to the battery. However, the battery, but in terms of the specific energy, it is much lower than the battery. Okay, and then we have a fuel cell here, which is also a good candidate. We have a very high specific energy, but a very low specific power. Okay, so if we decide to include the supercapacitor as the secondary energy storage, what we can do is that we can add that to the DC link of the battery here. Okay, which means that we add the supercapacitor here using another power electronic converters, which have a bidirectional power flow, which is in which the power and the energy can be controlled by controlling the voltage and the current of the supercapacitor using the controller here. Alternatively, we can connect the battery using to the DC link using the power electronic converters. But if we do that, then we add weight to the overall weight of the vehicles. If we do this configuration shown here, then we have no control over the voltage and current of the battery, but we have full control of the voltage, the current, and therefore the power flow of the supercapacitor. An alternative configuration is to use the fuel cell, which is getting popular nowadays, as the main energy sources, okay? Which means that the fuel cell is typically providing the average power, and the transient power is taken care by the battery pack, or alternatively, we can use the supercapacitor, or we can use the combinations of the battery and supercapacitors, okay? This is what is the current status in the world today of the usage of the electric vehicles. As you can see, again, China is leading the rest of the world, of the rest of the country, producing about 47% of the plug-in electric vehicles, which includes the hybrid plug-in as well as the full electric battery electric vehicles. This is the data obtained in 2019, okay, and followed by the rest of the countries. We have the European countries, the United States, and California, which is separated from the United States there, and Norway and the rest of the country. Interestingly, we see here that we have a Norway, which has the largest per capita usage of the electric vehicles. This is for every 1,000 people, which means that for every 1,000 people, 56 people in Norway uses electric vehicles. And it is far behind the rest of the country here, okay? China, even though producing the largest number of electric vehicles, but because of its large populations, has not that high per capita owner of the electric vehicles. This is another graph showing, at a different angle, and also separated between the electric vehicles and the plug-in hybrid electric vehicles, which shows the trend. For example, in China, we have a light blue here, and the dark blue which shows the plug-in, and the light blue shows the battery electric vehicles. The trend in most of the countries is that more and more electric vehicles is replacing the plug-in hybrid electric vehicles, okay? That includes China and the United States and the rest of the world. Let's look at on the success story of Norway, which has the highest per capita owner of the electric vehicles. What happened to this country actually? Okay, as of January to June 2020, 48% of the new registration cars are full electric vehicles. Okay, and then the government is heavily subsidizing and giving perks to the electric vehicle users. For example, the non-recurring vehicle fees such as the purchase tax and the 25% VAT is exempted from the electric vehicles. And also the electric vehicle users are enjoying the privilege of reduced road tolls, free parking, use of the bus lane, and so on. And their national transport plan has targeted that in 2025, all cars, buses, light commercial vehicles will have a zero emissions, which is a very ambitious target there. And then, which is also possible because 98% of the electricity produced in Norway is coming from the renewable energy, which is mainly coming from the hydro, 95%, another 3%, if I'm not mistaken, coming from the wind turbine, wind energy, and another 2% is coming from the coal. And what happened to Malaysia? Okay, we are not going to be that advanced compared to the Norway and the rest of the country, mainly because there are several obstacles, mainly because of the cost, which I have to be very quick here because of the time limitations here. For example, in 2013, Mitsubishi introduced a electric car, which is called iMe-EV, and up for that particular year, 2013, only managed to sell 30 units of cars, and they completely stopped in 2014 because it's not giving any benefits to them. The price at 1,336K, which is expensive compared to the the same class of the compared to the same class of the internal combustion engine car. We can travel for 150 kilometers with 5-year warranty. And then same day also Nissan introduced its Leaf model, which managed to sell 27 units up until 2019, okay, which is priced at 168K. And you also have to add an extra cost to install the charger at your home, which is another 6,500 around that cost. And in 2019, they introduced another model which can travel longer to 311 kilometers with a higher capacity of the battery and a whopping price of 188,000. Hybrid cars also not getting that high acceptance in Malaysia. The sales goes down from 13,000 in from 20,000 in 2018 to 30,000 in 2019, and it just contribute to 2.2% of the overall car sold in Malaysia. Okay, I think that will end the part one, and then I have to go quickly on part B of the talk, which is on our groups. We have 11 members in our groups. These are the list of the names. You can visit the website, and currently we have 18 PhD students attached to the group. And we have 3 laboratories attached to this research group. We have Powertronics Research Lab, which is located in P07. We have Electrical Drive Research Lab, and we have the UTM Proton Future Drive, which is one of the satellite laboratory for proton, which is located in P06. We have our activities, research activities ranging from electric vehicles to converter topologies and control, simulations, advanced control, and renewable energy system, which is listed here. Let me go through one by one quickly. Go through to the list of the members that we have very quickly. Okay, this is myself. I'm the associate. I'm the head of the PEDG. My research interest is mainly on the AC drives modeling control, and my current research is basically on the direct torque control and the applications of the model predictive control to the motor drives. We have Dr. Sharen, who has research interest in the experts in the inverter control design, multi-level inverter, and the maximum power point tracking algorithm for the solar PV, and also has expertise in the artificial intelligence, fuzzy logic applications control, and his current research interest in the boost multi-level inverter. We have Tan Chi Wei, Dr. Tan Chi Wei, whose research interest is mainly on the renewable energy systems, again MPPT, and the microgrid systems. Okay, his research interest currently is in his current research project is in the energy management of the long-term optimal capacity planning of grid-independent microgrid system using the multi-objective optimizations. And we have Zaki Daud, whose research interest, expertise in electric drives, including the work in the parameter estimations of the electric drive systems, Powertronics applications to the renewable energy systems, and his current research interest in the thermoelectric generator for charging mobile devices, and as well as the applications of the sliding mode control for the control system of the Powertrain systems. And we have Junaidi, Dr. Junaidi, whose research interest in Powertrain converters and electric vehicle applications. And his research project, current research project, is in the battery modeling and battery management systems. And we have Dr. Razman Ayub, whose research interest mainly again in the photovoltaic and the controller using the PI controller with particle of swarm optimizations, and also using the fuzzy logic controller. And his current research is in the simplified PV model with partial shading capability of a PV and using low burden and robust controller by simplified fuzzy logic controller. And finally, we have the Dr. Julia, whose research interest in the electrical drives and power electronics and vehicle to grid system, artificial intelligence applications to power systems, and a wide bandgap devices applied to the power electronic converters. And his current research is in the area of bidirectional power converters, vehicle to grid system, and the wide bandgap device. We have several activities conducted previously, but what I want to highlight is the one that we performed in 2012, which is the conversions of the internal combustion car into the full electric cars, which is used for the PGMC, which is the Proton Green Mobility Challenge, which is mainly performed by the undergraduate students and supervised by us, and which is headed, the project is headed by Dr. Shahrin. These are some of the pictures here. These are the architecture of the electric vehicle that we have constructed, which uses the conventional differential, the existing differential and manual transmission, which is fixed to the third gear, and we have a three-phase induction motor, replacing the internal combustion engine, using the Curtis controller and a 8 kilowatt lithium-ion battery, which is operated at 96 volts. We also have organized several conferences, which is known as the conference, the CENCON, Conference on Energy Conversions, from 2014. We conducted in Johor, 2015 in 2000, which is also in Johor, and then we moved to KL in 2017, and recently last year we have conducted this conference in Yogyakarta in 2019 in collaborations with the IEEE IPEL's Malaysia sections. And in 2021, we are returning back to Johor, and so I hope to see you there. We also have some linkage industries with the past and the present with Proton based on the MOU, NASA Motors based on the consultancy, and we also have recently collaborations, MOA with Nano Malaysia Berhad to develop the hydrogen-based electric vehicles. And I think that ends my presentation. I'm sorry for taking longer time because of the interruptions that we have just now. So I think I'll...
Okay. Okay. Thank you. Again, I would like to take this opportunity to thank to us, your Professor, Dr. Ni'um Zinik Idris, for sharing a very informative session. Now, I would like to open for question and answer session to all viewers. You can post your question to the Facebook Live here throughout the comment section. Okay, if you have any question, just post to the comments, so we'll answer your question. And then before we got one or two questions, so maybe I have one question here. In your opinions, why is the acceptance of EV is relatively low in Malaysia?
Yes, as I have mentioned previously, the main obstacle, which is basically conducted by a local researcher, they found out that the main obstacle is the price. Okay, the price of the EV, which is too expensive, which is unaffordable, higher than the much higher than the internal combustion engine price of the car, which I think the government has got to do has to do something with that in order to give more subsidies to the electric vehicle cost of the electric vehicles. And we know that some of us even struggle to buy the internal combustion engine car, which is also expensive due to the heavy tax. And secondly, according to the study, there is which is not only applicable in Malaysia, there's also a problem with what we call the range anxiety. People are afraid to use the electric vehicles because they are afraid that somewhere in the middle of the journey, they will run out of battery, which is also possible for the internal combustion engine, because you can also run out of petrol in the middle of the journey before you reach your destinations. But that is not a problem with the ICE engine, because if you walk a few kilometers ahead, then you see a petrol station in which you can refill your car. But that is going to happen with the electric vehicles, because it's not going to be that easy to refill the electric vehicle, to charge the battery, which means that we have to, at the same time, encouraging the use of electric vehicle, we also have to add infrastructure to the charging stations. And another third factor is, I think, is the education. We need to educate people why we need to use the electric vehicles, because of the global warming and the climate change. In fact, the price is a secondary factor. People use electric vehicles because of the global warming and the climate change. Some people, they normally select to use the electric vehicles because of the price. They say that they can save the energy and so on. But I think, in my opinion, the main reason we should use electric vehicles is because of the environmental concern. So education is very important, We should start to educate people right from the secondary school, even from the primary school, the importance of keeping the Earth temperature to a low value to avoid the global warming. Yes, I think that
Okay.
hopefully answer
All
the
right.
question.
So I think before, because I have another just one last question before we finish our webinar today. How can we encourage Malaysian to appreciate and reuse renewable energy system?
Yeah, that again boils down to the cost. I think the cost of the when we talk about encouraging people to use renewable energy, I think we meant the PV, okay, the solar PV, which is to use, for example, in our house. That again boils down to the cost. The cost of installation is too high. That will take longer time for the return investment period is long. And recently, the previous government introduced what we call the net energy metering, which is good because it is based on the concept of what's good. But the problem is that the installation of this PV, to the house is still expensive if compared to the other countries. For example, if you compare to the US, for example, to install a 3 kilowatt panel costs around 12,000 ringgit. Okay, but here in Malaysia, it will cost around 19,000 ringgit, which is much higher than that. So the government has to take some initiatives on subsidizing these PV installations, I think.
Okay. Anyway, thank you very much.
And
Yeah.
yeah,
Okay. Again, thank you very much to all viewers. Now I would like to pass over to Puan Sharifah Hauzaima for the closing of this webinar series and highlight our next webinar series for Research and Innovation, School of Electrical Engineering, Faculty of Engineering, University of Malaysia. Over to you, Puan Sharifah.
Thank you, Prof. Kamal. And thank you also to our guest speaker, Associate Professor Dr. Nek Rumzi Idris, for the interesting topic just now. Thank you, Doctor. All right, viewers, we are at the end of our session today. Thank you all for taking out time to watch this live telecast. And for those who missed this live session, can watch the video again in our Facebook. Don't forget to like, comment, and share our Facebook and videos to your friends and colleagues. And please don't forget to join us next week, 11th of August, 2:30 p.m. for the next series of webinar with our guest speaker, Professor Dr. Zaharuddin Mohammed, the head of Advanced Control Research Group, on the topic Current Research in Control and Mechatronics. All right, viewers. As usual, I will end this session with a quote. What good is an idea if it remains an idea? Try, experience, iterate, fail, try again, and change the world. Okay, dolls, keep on dreaming. See you all next week. Stay safe, keep your distance, and stay tuned. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Thank you.